In this video, we discussed how we could derive the entire wave function for our particle trapped inside the infinite square well. Now, when we're deriving this formula over here, we had this one term which is E, which represents the energy of your particle trapped in the infinite square well. But we did not discuss how or what were the allowed energies for your particle in the infinite square well. Your particle in the infinite square well can have some specific allowed states of energy in the square well, and that's what we are going to derive and discuss over here. Now, we know that our particle inside the infinite square well can be written down as a composition or a product as psi of x and phi of t, where psi of x is the position part and phi of t, which is over here, is called the time part of your wave function. Now, how do we derive or how do we come up with an expression for E? Well, we know that psi of x can be written down as the square root of 2 all over a times sine kx, where k is equal to the square root of 2me all over h bar. You can check my previous video where I derived this formula. I'll put the link down in the description below, and that will help you for a reference. Well, so this is your psi of x. Now remember that our boundary conditions demand that psi of 0 should be equal to psi of a, and this should be equal to 0. And if we plug this in, which means the values of x being 0 and x being a, we will find out that this basically implies that. Now, what this is basically saying is that the sine of k basically goes to 0 at the boundaries, which means the edges of your box. Since we have that the square root of 2 all over a times sine ka is basically 0, this helps us to write down that the sine of k times a is equal to 0, since the square root of 2 all over a cannot be 0, and we can divide both sides by the square root of 2 over a. And this implies that basically sine ka is basically equal to sine n times pi, where n is an integer. N is an integer. It can be any integer, but in this case we are only going to take into consideration that n is a positive integer. So I'll write this down over here as a superscript to help us understand that. All right, so since we can say that sine ka is equal to sine n pi, we can take the sine inverse of both sides, and then we can write that ka is basically equal to n pi. And if we separate out k, this leaves us with k being equal to n pi all over a. All right, so we have an expression for k all over here. Now, recall that we also defined our k to be equal to the square root of 2me all over h bar, right? So if we equate this equation 1 and equation 2, set them equal to each other, which they basically are, we can deduce that n pi all over a is equal to the square root of 2me all over h bar, right? And by squaring both sides, we can say that n squared pi squared all over a squared is basically 2me all over h bar squared, right? Now, see over here, if we solve for e, then e becomes a function of n over here, right? So if we solve for e sub n, I'll write down e sub n since it's a function of n, we can say that e sub n is basically equal to n squared pi squared h bar squared all over 2ma squared. So what this basically tells us that your particle inside the box is a function of n, where n is basically any positive integer. N cannot be 0, it's any positive non-zero integer. But this looks very mathematical, and it doesn't really help us visualize what our wave function is doing, right? So in order to give you a more visual sort of an effect of what's going on, we'll try and understand what our particle is doing inside the infinite square well, having different sorts of energies. So as we know that our E is a function of n, where n is basically 1, 2, 3, dot, dot, dot. Let's see what happens when we plug in n is equal to 1. Well, n is equal to 1 would give us a value of E is equal to pi squared, h bar squared, 2ma squared, and then E is equal to 2, n is equal to 2 would give us something like 4 pi squared, h bar squared, 2ma squared, and the values will go on. So what happens to our wave function is that if you plug in n is equal to 1, of course this is our infinite square well, I should make that very clear. Let me use a different ink. This is our infinite square well, and if we plug in n is equal to 1, then our wave function kind of goes like this. All right? But then again, when you do a value of n is equal to 2, your wave function kind of looks like this. N is equal to 2. And then for n is equal to 3, we will get something that goes like this. Basically tells us is that if your particle has an energy at n is equal to 1, then you will have two nodes in this graph over here. For n is equal to 2, this will have 3 nodes, more specifically this, and this. And then for n is equal to 3, you'll have 4 nodes, and this will go on. This is basically helping to visualize what's going on over here. Now, one very interesting thing that I observed when I first encountered this is that, well, this basically represents how your wave function looks like, right? Whatever I'm drawing over here, this is your psi of x, right? Now, what we know is that when you take the integral of psi conjugate times psi dx, and you basically set limits from 0 to a, you get the probability of finding your particle in between 0 and a, right? What's interesting is that at the points where the nodes exist, your particle cannot be found in that particular spot. And this is very interesting because you'll find a particle in this region, you'll find your particle in this region. However, your particle cannot be found at this particular spot over here. Pretty interesting, right? Well, that's basically it. You know that your allowed energies for your particle is basically E sub n is equal to n squared, pi squared, h bar squared, all over 2m a squared. Hope this will help you understand allowed energies of particles even better. And yeah, that's all.